Good morning and good evening, depending on where you are from. So my name is Bhanuka. So I'll be presenting our paper on GazeNet, which is for appearance-based gaze estimation using Capsule Networks. So my name is Bhanuka Mahanama. I'm from All Dominion University, Norfolk, Virginia, and my co-authors are Yasid Jadhav, who's also a PhD student, and my supervisor, Dr. Sampath Jayaratne, from All Dominion University. So this is the outline of my presentation today. So uh, I will be first going through some introduction and related work relating to the appearance-based gaze estimation, and then I will be talking about our approach here and our proposed architecture, and finalizing with our conclusion on the study. So if we look at the gaze estimation, so in general we talk it as eye tracking as well. So gaze estimation has multiple applications. So one major application is the physiological studies, so where we can use gazes or the eye tracking behavior or changes in the eye movements for physiological studies, such as detecting the ADHD and non-ADHD and PTSD as well. And we also have gaze estimation in the form of a computer human interaction, so where we can provide gaze as an input to the system as a form of interaction. So if you look at the modern methodologies in eye tracking or the gaze estimation, so modern methodologies focus mainly on appearance-based gaze estimation because it does not need specialized hardware or software. And yeah, usually these methods tend to use convolutional neural networks. And as the input of these systems, they use either facial regions or ocular regions depending on the model they are using. So if we take a look at the related work for a gaze appearance-based gaze estimation, if we move back in time, uh, the previous methods usually relied assumed that there's a fixed head pose, and so as a result, they did not account the change variability of head pose into their studies. And with the time, in with the modern approaches, they accounted those variability in the head pose to the model. So in the case of accounting those variability of head pose, they used either explicit head pose information, such as we are giving the model the calculated head pose as a separate input in addition to the images. And in some models they have implicit head pose information where the model itself extracted the head pose information based on the images. So taking a look at the training methods on these methods, usually these methods tend to be data-driven approaches where we build a model based on entire data set despite of the users. And we also have user-specific scenarios or user-specific training methods where we ask the user to do some form of interaction with the device or a screen, and based on those events, we capture the gaze locations and train it according to the user. So our approach here is to use build a model that can do the gaze estimation. So using the capsule network. So in the case of capsule networks are initially, or original idea of capsule network is for the estimation. So in this scenario, the gaze estimation is a regression task. So we will be our approach here is to follow a two-step approach where we first classify the gaze estimation, and based on the classification, we do the estimation. So at the first step, so this is our architecture for the model. So first step is we have a couple of convolution neural networks. Then we pass that to a capsule network, which has two layers: primary capsules and secondary capsules. So in the case of secondary capsules, we generate the gaze classification. So gaze classification, we classify the gaze into six regions as left top, middle, top, likewise into six regions based on the data or the values represented that's accumulated in the gaze caps layer. We pass it to the gaze estimation. So uh, for the estimation, we used a fully connected neural network, as you can see. So it gets the information from the gaze caps layer and pass it to through a fully connected neural network with three layers and do the gaze estimation. We also do a form of reconstruction, image reconstruction. For that as well, we use a fully connected neural network. So this is our function for the margin loss, our loss function for the new entire network. So we have three terms. First term is the margin loss, second term is the reconstruction loss, and third term is the estimation loss. So in the margin loss is corresponding to the accuracy of the gaze classification. So reconstruction loss corresponds to the pixel wise error in the image reconstruction, and estimation loss corresponds to the error in the gaze estimation at the estimation network. So by tweaking the values of lambda 1 and lambda 2, we can get different forms of regularizations and different conditions required in training. So we use reconstruction and estimation as the form of regularization for the entire network. So for training and testing, we use the MPI gaze dataset. So as you can see on the right, you can see some samples from the MPI gaze dataset. So we use the processed images. So where they have processed the entire, where they have cropped eye regions or ocular regions into 60 by 36 image patches in the grayscale images. And we also use that dataset for our testing purposes as well. In addition to that dataset, we also use a smaller dataset, Columbia Gaze dataset, which is around 5,000 images for testing purposes as well. So our first experiment is to testing on the MPI Gaze dataset. So for measuring the performance of our model, we use accuracy, which corresponds to the gaze categorization at the gaze caps layer. And we also use gaze estimation error as another metric for measuring performance of our model. So and when conducting the experiments, we conducted our experiments under four conditions. So first one is the no regularization. So in that case, both lambda 1 and lambda 2 in previous expression is 0. And we use only gaze estimation as a form of regularization, then image reconstruction as a regularization, and combination of both estimation and reconstruction as a form of regularization. So these are the results we were able to obtain. So our accuracy with no regularization was the highest, so it was 67%, and mean absolute error in our estimation was around 2.84 for the combined regularization. So at the bottom, you can see some of the reconstruction images. So bottom-most images are the original images, and the upper images are the reconstructed images. So as you can see, our model has been able to capture some of the vital informations in the model, information in the ocular regions, and it has been able to regenerate those images based on the capturing or the representation that is available in the gaze capsule layer. So then as the second experiment, we performed experiments on transfer learning. So in the case of transfer learning is where we apply a knowledge from a previous problem to another problem. So in this case, we have the knowledge acquired from the MPI gaze dataset. So we are going to apply that knowledge onto another dataset, which is the Columbia gaze dataset. So here since the Columbia gaze dataset has facial images, so we had to crop those images to get the ocular region. So for that, we used a library called POSNet, which is a TensorFlow library, which is readily available. And we conducted per participant experiments. So through that, we kind of test how the transfer learning can be performed on a personalization basis. So this is our transfer learning experiment. So we conducted our transfer learning experiments under two main conditions. First one is no retraining. So in this case, we just pass the images in the network we have trained and obtain the mean absolute error for the estimations. And in the second condition, we retrain only the estimation network, which is beyond the point of the gaze caps. So in that case, we trained only those smaller portion of the network, and we froze the entire network before that portion. So our mean absolute error in estimation is with no retraining, we had 10.4. 0.04 degrees of absolute error, and with retraining we were able to make it half, around 5.92. So our discussion on the main key takeaway is that we can decode the head pose from the ocular images, and we can decode the eye rotation of the of the gaze, which is relevant to the gaze, using ocular images. So if you can, so onto your right, you can see some of those parameters by some of the images reconstructed using tweaking some of the parameters in the gaze caps layer. So as you can see, the first row is first by in the first row you can see, by tweaking some parameter in the gaze capsule layer, you can see that the description of the eye moves from left eye to right eye. So as you can see, the leftmost image is a eye of a left eye, and rightmost one is a right eye. Likewise, and likewise we have different each in each parameter, the model has able to capture some of the key informations that is present in the ocular images. And we another key takeaway is that we can use transfer learning for personalization. So in this case we use knowledge from MPI gaze dataset, which is a larger dataset, and we personalize.
Please wrap it up.
Huh? Sorry.
Time is up. Please
Okay.
wrap your talk.
Okay. So we applied for a smaller data set. So that's out for my presentation. So if you have any questions, you can ask them now, or you can contact us through either Twitter or maybe through email. Yeah, thank you.
Okay, thanks, Bhanuka. Great talk. Any questions for the presenter, please? Just use the chat to ask your questions. While waiting for questions, let me ask you one. In one of your slides, you showed that the accuracy is 67%. Why it is so low?
Yeah, the problem here is that we use so if we go to the architecture, so we are using a CRISP classification. So imagine the input gaze is to the bottom of the left top image. So the model classified it as a left bottom, and actually it is a left top, but it is somewhere in between. So both of those are kind of valid in the perspective of the model, because it is closer to the left bottom. So something like that. So we have proposed a non-CRISP classification. So we have kind of worked on that as well.
Okay, thanks. Since there is no more questions yet, I will ask a follow-up. What are you? What is the? You said one of the metric is accuracy. What you mean by accuracy?
So in this case, accuracy means the correct classification that we get from the gaze caps layer. So each of the different categories in the gaze caps layer corresponding to different. So we have six capsules. That means six capsules represent six directions of gaze. So if the model correctly classifies, or the gaze capsule corresponding to that classification is higher, that means it is accurate like this.
Still, the accuracy is rather low.
Yeah, it's because of those because of the CRISP classification we have used. So imagine it is some imagine the actual gaze is somewhere between imagine the classification in the dataset is left top, but actually it's more towards the left bottom. So in that case, the model actually might classify it as left bottom, but it is incorrect according to the data set. But is at the point of view of the model, or actually since it is closer to the left bottom classification, it is correct, kind of. So we have to take into that as well, because so in such scenario the model will be penalized, because it is the according to the data set it is left top, but actually it is more towards the left bottom likewise.
Okay, thanks a lot. And there is no further questions, I guess, and we just are on time still. So thanks again,
Yeah.
Bhanuka, and
Yeah, thank you.
the great work. We hope to see the follow-up and more better results in the accuracy and other things. Thanks again.
Yeah, okay, thank you.